Okay, welcome back, everyone. In this video, we're going to take a look at this concept called Poisson's ratio and also a concept called shear modulus. But let's start off before we get going with a short review of where we're at. We had talked about stress. Remember, stress is, hold on here, can't write today, is force over area. And we talked about this concept of strain being the change in length over the initial length. And then what we said is we have this concept of a stress-strain relationship. We called that our modulus elasticity, stress over strain. And we talked about this graph here where we have our stress on the vertical, our strain on the horizontal, and we can map out different materials. And we talked about this elastic region, and really this is where we're going to be operating pretty much this whole semester is in this elastic region, which means that our E value, which is the slope of the line, the modulus elasticity, will be constant, and it can let us do a whole bunch of cool things. So we talked about this. We said what E is. We said stress over strain. We talked about units. Well, now, if I am pulling on an object like I see down here, in this case, this cylinder, it's getting longer, right? That's our strain that we've already talked about, our change in length, our delta. Well, in a way, what you can think of what's happening is if that material is getting longer, it's also going to get skinnier, meaning the content, the stuff that it's made out of has to go somewhere. So if you're increasing the length, you're probably going to decrease the diameter. There are a few materials that don't obey that, but for the most part, that's the way it works. So what we can have is we said we have this delta. Let me use a different color. That blue, I have too much blue in here already, but this delta is our change in length. Well, I'm going to put a negative delta prime. Delta prime means our change in diameter. So it's getting skinnier, right? So it gets longer and skinnier. We've already defined this idea of strain, but I'm going to add a little subscript and call it longitudinal strain, longitudinal being along that long axis. We already said it's the change in length over the initial length. And because now we have two different directions, that's why we're calling this one longitudinal and the other one being latitudinal, where we're transverse to the direction of that force. So latitudinal strain is, like I said, equal to this delta prime, the change in diameter over the initial diameter. I think that's the easiest way to try and write it. Well, there's this concept or this property called Poisson's ratio based on the material, on the relationship between how much skinnier it'll get based on how much longer it gets. Of course, all this assumes we're in tension. If it's in compression, same idea. If it were in compression, it would get shorter and it would get fatter, right? But regardless, that's why this little negative is in here, because we have that relationship. As it gets longer, it gets skinnier, or if it gets shorter, it gets fatter. Regardless, we have Poisson's ratio. It's the symbol for this is the Greek letter nu, which is that kind of sideways V looking thing, right? So let's take a look with an example of how we do something like that, or how we use it. Let's say that we had a bar like this. This bar has dimensions of 50 millimeters tall, 100 millimeters wide, 1.5 meters long, and we put a force of 80 kilonewtons on this bar. We're giving it steel with a modulus elasticity of 200 times 10 to the third, which is steel. Poisson's ratio can be looked up. It's usually right around in the 0.3s, and this steel is about 0.32. And then we have a yield stress at 250 megapascals. And we want to find out what would the final dimensions be after I put on that 80 kilonewton load. So the first step is we want to start off by finding out how much longer it's going to get, right? So that's our axial direction. And within our axial direction, we already know that we have a stress, which is equal to the force over the area. And we always want to be working in metric. We want everything in newtons and millimeters. So we have 80,000 newtons, which is our 80 kilonewtons. And then our cross-sectional area. So what cross-sectional area means is if I were to cut it, what does that look like? What's that cross-section? So we have 50 by 100. So 50 millimeters by 100 millimeters. Mathematically, if I put that in, I ended up with 16 megapascals. And if we go back up here, we see that our yield is 250 megapascals. We're only at 16. What are we checking? We're checking that we're still in this area because we just found our yield point. Are we below that? Yeah, we're way below because we're way down here at 16 and up there is all the way up at 250. So it's a good check. I'm not going to actually make you check or have you check or try and trick you on an exam or anything. But regardless, it's good to know that we're in that elastic region. All these equations still work. So we end up with sigma is P over A gives us 16 megapascals. And we have our relationship between stress and strain with our modulus elasticity, which is equal to stress over strain. So I can arrange that and say that my longitudinal strain, because that's really, now that we're talking about longitudinal and latitude, I shouldn't do L because they're both L, right? Let me do longitudinal. Let's do this. Longitudinal strain. Then rearranging that equation is equal to the stress over the Young's modulus, modulus elasticity. So we have that 16 megapascals over our E value for steel is 200 times 10 to the third. That's also megapascals. So our units work out because we want a unitless value for our strain. And what did I get here? I ended up with 80 times 10 to the negative sixth millimeter per millimeter. Now that isn't the change in length, that's just the strain, meaning it's change in length per length. To get my actual change in length, my delta L, how much longer does it get? I have to take that strain, that longitudinal strain, and multiply it times the initial length, which is that 1.5 meters. So I'm starting off with this 80 times 10 to the negative 6 is my strain. My initial length is this 1500 millimeters, since we want everything to be in millimeters. And that gave me, what did I end up with? 0.12 millimeters, 0.12 millimeters. And of course, it's getting longer, right? Because we're stretching it. We put a tensile force on it. So yeah, so these numbers are pretty much always going to be pretty small. There isn't a lot of stretchy deformation. Otherwise, things get a little tricky. But for our purposes, these numbers are always going to be pretty small. So you might have to carry some extra digits to really see what's going on. But 0.12 millimeters longer in that longitudinal direction. So that's in the axial or longitudinal. I guess I should put that in there. I did in my notes. Longitudinal. Let's look at transverse or latitudinal direction. Transverse, meaning how much skinnier is it going to get, right? So the transverse, which is the latitudinal. So we start off by, we need to figure out our strain. Well, we know our longitudinal strain, and now we can find our latitudinal strain by this new concept of a Poisson's ratio, because we know it's negative E lat over E long, right? So from that, I know that my latitudinal strain, if I just multiply both sides by E long, is equal to negative Poisson's ratio times E long. So that gives me a negative, what is our Poisson's ratio for this? 0.32 times this longitudinal, which I just found to be 80 times 10 to the negative 6 millimeters per millimeter. Multiplying that through, what did I get? I ended up with something like minus 2.56. These are very small numbers, so I went to scientific notation. Times 10 to the negative fifth millimeters per millimeter. So that's my latitudinal strain. Well, now what does that mean? Once again, that's not the change in dimensions, but I can use it with my original dimensions. That was really weird. But anyway, so I have 50 and 100. So this is how much thinner it would get or how much shorter it would get, right? Those are both transverse to the direction of the loading. So there's really two different dimensions. One is the height. Clearly, it's got to get shorter, right? So if I look at my height, let's say delta H, how much height is going to change is equal to that latitudinal strain. times my initial height. So we have that minus 2.56 times 10 to the minus 5. I'm going to leave out the millimeters per millimeter because we know what we're doing now, right? We're pretty solid. And then I started off with initial height of 50 millimeters, and I ended up with a negative 0.00128. Like I said, these are little bitty numbers. They even get smaller when you go in that latitudinal direction. Of course, this is getting shorter, right? I mean, it's almost like a double negative because I already have the negative in there. Maybe I don't need to put that in there, but whatever you need to do to keep it straight, that it is getting smaller in that direction, because what we see is an overall volume change. The volume isn't consistent. The volume does actually change, but the volume is growing based on the length, but shrinking based on those transverse directions. All right, so we get a little shorter. We also have a change in our width. And with our width, we have a delta W, or change in width, is equal to that same ELAT value times our initial width. So that same minus 2.56 times 10 to the minus 5th times our initial width of 100 millimeters. So I end up with minus 0.00256 millimeters, right? And of course, that's going to be thinner. I don't know if I need to put that in there, but regardless, we have two different dimensional changes here. I guess I could, so we keep it straight. Which direction it's going, I don't know. Regardless, there we go. So looking at the final dimensions, we see that it got 0.12 millimeters longer. It got negative, or 0.00128 millimeters shorter, and 0.00256 thinner. So we could find the total volume difference between the two, but it wasn't really asked for in the problem. So yeah, so hopefully that made some sense. One last little quick concept we're going to cover. I'm not even going to do an example problem here. It's just a short little thing. And this is the idea of a shear modulus. It's also known as the modulus of rigidity. We'll deal with this later in this semester a little bit more, but just to introduce the concept, this is very similar to when we looked at our relationship. Remember this whole thing where I had stress and strain, and let's see, stress and strain, and I had this E value, right? And we said that E is equal to stress over strain. Well, this is the same idea, only with instead of a axial stress, we have a shearing stress. So we see in this, let me go back over to this laser pointer deal. So we see over here we have a block, and we're putting a shearing stress, meaning it's parallel to that surface, and we're pulling it over. And what we see is we get this deformed shape. And then that deformed shape, we can look at this angle here for our shear strain. So all that should be reviewed. We've already talked about all of this, shear stress, shear strain. The only new concept here is we have Hooke's law once again, but instead of E is equal to stress over strain, we have G is equal to stress over strain. But it's the exact same thing, right? Instead of axial stress, I have shear stress. Instead of axial strain, I have shear strain. So yeah, in shear modulus, modulus rigidity, you can look it up in any properties table based on your material you're looking at. And there is a relationship if you have two of the three, meaning if I have the modulus elasticity and I have Poisson's ratio, I can find that modulus of rigidity, or you can rearrange it in any way to get the other two. So just another concept. Like I said, we'll talk more about that later, but just so you get introduced to it right now, shear modulus. All right, so that's all I have for this one. Hopefully that all made sense, and I look forward to talking to you all next time. Thanks for tuning in.